hope you guys had a great break. We're going to start this year off with conservation of momentum. Now, we touched on this last semester. We talked about conservation of momentum, which we said that the momentum, which was our capital letter P, equaled mass times velocity. The momentum of a system before had to equal the momentum of the system after. Well, all we dealt with last year, or last semester, was momentum in two dimensions, or excuse me, in one dimension, meaning that everything was going along the x-axis. So we had two cars that hit, and then they went off in the x-axis. Today we're going to talk about conservation of momentum in two dimensions, which means we're going to be dealing in the x and the y. And this is more realistic. Okay, so here's a picture. So if you're driving your car down Wickham Road here, and you hit Vieira Boulevard, or let's say you have Vieira Boulevard here, and this is Stadium Parkway. So you're driving down Stadium Parkway this way, and some old lady comes and drives right through the intersection and hits you. Well, that's more realistic than to be rear-ended and end up going in the same direction. In this case, what's going to happen? Well, the velocity of A and velocity of B are going to come together, and chances are they're going to head off in some direction that way. So right away we have the car A is going in the x direction, car B is going in the y direction, and then off together they go somewhere in between. So what we're going to have to do now is we're going to have to work in the x and the y, either one. We cannot work together, just like we couldn't do when we talked about projectile motion. We could not combine the velocities and say that they were in the x and the y together. You had to break them down into their components. Okay, so remember that the momentum is a vector. Therefore, because it's a vector, it's going to have magnitude and direction. The magnitude is easy for us to figure out. It's just the mass times the velocity. So the magnitude of car A is just the mass of car A times the velocity of car A. The momentum of car B is the mass of car B times the velocity of car B. That's not a problem, but the direction, we have this is going to be in the x direction, this is going to be in the negative y direction, and their final velocity is going to be somewhere in between. So the way that we add vectors is just like we did back at the very beginning of the year. We add vectors tip to tail. Now it runs into a problem. Remember, if we did tip to tail addition of vectors, we would need to have graph paper or an awful lot of room, and we have neither. So what we're going to do is we're going to add vectors. Instead of tip to tail, we're going to do it algebraically. The way that we add vectors algebraically is breaking everything down into their x components, adding all the x components together, and then breaking everything down in the y components and adding all the y components together. Okay, so let's look down here. And a good example here would be, we have maybe two pool balls, okay? So if you can kind of picture, here's your white ball and here's one of your solids or your striped balls. You're going to hit the white ball. Now this ball right here is not moving, so the velocity is 0. This is the before situation. Well, what's going to happen is ball A is going to hit ball B, and they're both going to go off in different directions. They don't stick together in this case. So ball B is going to head off here with a final velocity B, but it's going to be at an angle of theta B. Ball A is going to head this way with a final velocity of VA final, and it's going to be at an angle of theta A. Now these thetas are not necessarily the same, and either are the final velocities. So what we're going to do is we're going to do the same thing that we did before the break in one dimension. We're going to talk about the momentum before the collision or the contact has to equal the momentum after the collision or the contact. So what is the momentum before? Well, the momentum before is going to be the momentum of A plus the momentum of B. Well, the momentum of A is just the mass of A times the velocity of A. The momentum of B is going to be mass of B times velocity of B. Well, the velocity of the B is 0. So this one just kind of crosses out and that becomes 0. Now the final velocity, the mass of A times the V final of A, plus the mass of B times the V final of B. And that's what we're going to end up doing. Now the problem that we have is this V final of A and the V final of B are not in the same direction as the initial velocities of these. This is in the x direction. So when we make them equal to each other, we have to say that the x component of this has to equal the x component of that, and the y component equals the y component. Okay, so what we're going to do is we're going to set up a table. Now this is just a way that I have found that it makes it easier, just like when we did the projectile motion. This doesn't necessarily have to be the way that you do this. But momentum is a vector, once again, so we have to break it down in its x components. So we're going to take that same situation and we're going to say that we have the mass of A times the velocity of A. That's the initial ball. If we remember, the ball A was coming this way. Ball B had an initial velocity of 0. And then after the collision, we have A heading this way at VA final. And B is heading this way at VB final. Okay, and these were theta A and theta B. Okay, so the initial velocity here is, the initial momentum here is just ma times va plus mb times vb, but that is 0. So plus mb vb, and that ends up being 0. And this is only in the x direction before. Now if we stick with the before, and now what is the y momentum? Are these balls, either of them, moving in the up and down or the y direction? No, because this one's only moving here. So we have MA, VA in the y, which ends up being 0, plus MB, VB in the y, which is also 0. So the momentum before is 0. And I know that sounds kind of weird, but that's okay to have that. Now let's look at the after. Now we're only talking about the x components. So we're going to say the mass of A times the velocity of A final, and we're only talking about in the x direction, so we're going to do cosine. So cosine theta A. And we're going to have to include that one. And this is a positive x direction, and this one is also positive. So we'll have MB, VB, cosine theta B. Okay, and this information would be given to you, and so you could easily figure it out. Now let's talk about the y direction. Well, it initially starts off with no momentum in the y direction, and now we're going to do the same thing. We're going to write it just like we did before, but instead of in the x direction, it's the y direction. So the cosine changes to sine. So we have sine theta A. Now is that sine of this going to be positive or negative? Well, the component's going here, and if we were to push it on the y-axis, it would go up, so it's positive. What about this one? If we push this to the y-axis, it's going to be pointing down, so it's going to be negative. So we're going to say minus MB VB sine theta B. Okay, so now we have two equations, and that's really good because the two unknowns that we have would be our V finals, and we could be able to solve this. Now I'm not going to follow it through because we really don't have any information in there, so what I'm going to do is we're going to do a problem right now and actually solve for some unknown variables. Okay. So here's our example. We have a 975 kilogram car, and we're going to call that car C, and it's moving south. So it's going to be moving in a negative y direction at 22.5 meters per second. So our given is going to be the mass of car C is 975 kilograms, and the velocity car C initial is going to be 22.5 meters per second. Now, is that going to be a positive or negative? It's going to be negative. Okay? And it collides with the 2165 kilogram truck D moving west at 17.5. So we know that mass of D is equal to 2165. And we know that velocity of D initial is 17.5 kilograms. And once again, it's in a negative direction. Okay, they stick together. So after the collision, you can see that they hit. they stick together. So that means that their final velocities are going to be the same. They stick together, and what direction and with what speed do they move after the collision? So what we're looking for here is this angle theta and this speed v. So we have two unknowns, theta and v final. So that means we need two equations. Okay, so let's start off and actually solve this. Okay, so we're going to have our before and our after. We're going to have our x direction and our y direction. Okay, so before we have car C that's moving this way. So what is the momentum of car C in the x direction? Well, it's only moving south, so it's going to be 0. So we're going to have mass car C times velocity C in the x, which is 0, plus mass of the truck D times velocity D in the x. Well, we do know what that velocity D is in the x, and we know that it's negative, so it's going to have a negative number right here. Okay, now let's talk about the momentum in the y direction. Well, car C is going down, so we have a negative mass C, VCY, and D is only moving in the west, so it would end up being plus 0. Okay, so if we clean this up here, we'll erase that, and we are going to erase this. So this is what our initial momentum looks like in the x and the y. Now let's talk about the after momentum. Well, the mass of the collision is going to be the mass of the car plus the mass of the truck. So we have the mass of the car plus the mass of the truck times the v final. And this is what we're looking for. But now we're looking for it in the x, so we're going to do cosine theta. Okay, so this is an unknown also. And what is it going to be, positive or negative? Well, at the end, we said that it went off in this direction. Okay, and this is our theta. So if we push this v final to the x-axis, it's going to be negative. And let's talk about the y. It's going to be the same thing, the mass combined times the final, and it's in the y, so it's going to be sine theta. So we have the two unknowns again. And once again, if we push this vector to the y, it's also going to be negative. Okay, so now we have our two equations and our two unknowns. So let's go ahead and actually try to solve this. Okay, we're going to say that the before in the x equals the after in the x, the before in the y equals the after in the y. So we have negative mass of the truck, v of the truck in the x equals negative mass of the car plus mass of the truck times v final cosine theta. Okay, so that's one of our equations. Okay, so let's put some of these things together.